Hello, this lecture begins our coverage of Chapter 4 materials. In Chapter 3, we looked at Pick 24 instructions for doing addition, subtraction, as well as for increment and decrement. In this chapter, we're going to look at instructions for accomplishing right shift and left shift, bitwise and or, exclusive or, and bitwise complement. We will not look at Pick 24 instructions for doing either multiplication or division. A bitwise AND operation of two variables is written in C as K ampersand I. These three forms of the bitwise AND operation share the same addressing modes as the add and subtract operations covered in the previous chapter. This form of the bitwise AND operation takes a 10-bit literal, ANDs it with a working register, and writes the result back to the working register. A bitwise inclusive OR operation is written in C as K pipe symbol I. These forms of the bitwise inclusive OR operations mirror the forms of the bitwise AND operation. A bitwise exclusive OR operation of two variables K and I is written in the C language as K up hat symbol I. These bitwise exclusive OR instructions use the same addressing modes as the bitwise AND and inclusive OR operations on the previous slide. A bitwise complement operation of a variable K is written in the C language as tilde K. These addressing modes for the bitwise complement instructions are the same addressing modes as used for the increment and decrement operations discussed on the previous chapter. Finally, a couple other operations that we want to discuss are the clear and set M instructions. The clear instructions clears all the bits of its target operands. For example, this will clear all the bits in a memory location. The set all bits operation, as represented by the set M instruction, is the opposite. It sets all the bits in the target operand. Let's take a look at some of these bitwise operations. First, we'll take a look at the bitwise AND operation. What this is useful for is used for clearing a group of bits. In this example, we have an 8-bit variable I, and we're going to AND it with the value 0f. A bitwise AND operation, if you recall, if I take a 1 and AND it with something, I will get the same value. If I take a 0 and AND it with a bit, I will always get 0. So 1 ANDed with anything is the same as anything. 0 ANDed with anything is always 0. So in this case, what we have is we have the upper 4 bits of this literal, which I'm going to call the mask, are all zeros, while the lower 4 bits here, F, are all ones. If I take some numerical value such as this, 2C, what's going to happen is that wherever the mask bits are 0, that's going to be cleared to 0. Wherever the mask bits are ones, I'm going to leave that value unchanged. So in this case, a 2C ANDed with a 0F is going to result in a 0C. To do this in Pick 24 assembly language, I'm going to move the literal value 0F and the W0. Then I can do this operation here, which is going to take the memory location, AND it with the working register, which is W0, and it's going to write the result back to I. The end result is that I is going to equal to I ANDed with this literal value. While the bitwise AND operation is useful for clearing a group of bits, the bitwise inclusive OR operation is useful for setting a group of bits. So let's review the rules of the OR operation. If I take a 1 and I OR it with anything, that is going to always give me a 1. If I take a 0 and OR it with anything, that is always going to give me back my same value. So 1 ORed with anything is a 1. 0 ORed with anything is anything. So let's take a look at a numerical example. We'll take this 8-bit variable J. We're going to OR it with this constant value 0e. And if we have J equal to 0xb2 and our constant value is 01e, what's going to happen is wherever our mask bits are 0, the equivalent bits are going to be unchanged. So these are unchanged, as well as this bit right here is unchanged. Wherever I have mask bits as a 1, these bits right here will be set to a 1. So my end result is B2 bitwise OR to 0e is going to be a BE. In Pick 24 assembly language, this solution here is exactly the same as the solution on the previous page for the bitwise AND operation. Let's discuss the bitwise exclusive OR operation, which is useful for complementing a group of bits. The rules for bitwise exclusive OR is the following. If I take a 1 and I bitwise exclusive OR that with a bit, that will produce the complement of that bit. A 0 exclusive OR with a bit will leave that bit unchanged. So 1 exclusive OR with anything is the complement of anything. 0 exclusive OR with anything gives anything. This example is going to take an 8-bit variable k, bitwise exclusive OR with a constant, which is going to be the mask. So let's take a look at a numerical example. Let's let k be 8a. The mask is C0. Wherever the mask bits are 1, as in this case, these two bits right here will be complemented. So a 1 will become a 0. This 0 will become a 1. Wherever the mask bits are 0, these bits in this operand are going to be unchanged, so these are simply copied down to here. Our final result is going to be a 4a. The PIC24 microcontroller a solution for this in assembly language is the same as the previous two solutions for bitwise and bitwise inclusive OR. This slide shows an example for the bitwise complement instruction. Here we're going to take a numerical value of 8a, which is written in binary as this. The bitwise complement is simply going to flip every bit, so a 1 becomes a 0. These three 0 becomes 1. A 1 becomes a 0, 0 becomes a 1, 1 becomes a 0, 0 becomes a 1. The end result is going to be a hex 75. This instruction form right here is simply a complement, bitwise complement the contents of memory location K. The PIC24 instruction set also has some efficient instructions for clearing, setting, and toggling only one bit of memory or a register value. We can do that using the previous bitwise operations that we looked at, but it will take multiple instructions to do so. These are the various instruction forms of these instructions. We'll just look at one. A bit set of a working register where we give an immediate that says what bit to set. This can only be a working register, can also be an indirect addressing mode. This is going to end up setting a bit in a memory location. This slide gives numerical examples for the bit clear, bit set, and bit toggle instructions. Our aim is to have some 8-bit variables, and we want to clear bit 7 of K, set bit 2 of J, and complement bit 5 of I. In C, we would write it as this using these particular mask values, and we could implement this using the previously covered bitwise logical operations as shown in the previous slides. However, using the bit clear, bit set, and bit toggle instructions, we can also accomplish each of these operations using only one instructions. So in this case right here, we want to clear bit 7 of K, so we're going to specify the literal value here, number 7. Let's take a look at a numerical example. So let's let K equal 8a. Let's find bit 7. That's bit 0, 1, 2, 3, 4, 5, 6, 7. We're going to clear this bit, so our result is going to have this bit cleared to a 0. So our final 8-bit result is going to be a 0a for K. This is going to bit set bit number 2 for J. So let's have J contain a B2. So bit 2, that's bit 0, bit 1, bit 2. We're going to set this bit in the result. So our final 8-bit value is going to be a B6 for J. Finally, we're going to toggle bit 5 in I. So here's the numerical value for I is a 2C. So bit 0, 1, 2, 3, 4, 5. We're going to toggle that bit. That's going to become a 0. Our final result is going to be a 0C for I. If these were 16-bit variables, then we could complement any single bit in those 16-bit variables, and these literal values could range from 15 to 0, and we would drop the dot byte if we were doing a word operation. Let's begin discussing a very important special function register that we have ignored up to this time called the status register. The status register contains some 1-bit flag values that can be set or cleared. These particular flags here can either be user set or cleared, but they are also set or cleared as a side effect of instruction execution. This chapter is going to concentrate on the carry and 0 flags. The next chapter will discuss the negative and overflow flags. When we talk about interrupts, we'll talk briefly about these flags, and we will not discuss either this flag or this flag. the carry and Z flags are two flags that are set as side effects of particular instructions. They can also be set or cleared explicitly using the bit set, bit clear instructions. So how do you know if an instruction affects the carry and zero flags? Well, you need to look at the information up in the PIC 24 data sheet, or you can look at the information up in Appendix A in the textbook. As an example, the add instruction, which is an arithmetic instruction, affects all of these flags, and in general, most arithmetic instructions affect all of these flags, while the move instruction affects none of these flags. And when it says it does not affect it, it means that whatever their values are going into the move instruction, the same values are retained after the move instruction. This particular form of the move instruction, which copies the contents of memory location to itself, and which we thought was a useless instruction, is actually a useful instruction because it affects the zero and negative flag, and this is an easy way to check to see if a data memory location contains either a zero or a negative value. Let's discuss how addition affects the carry and zero flags. The zero flag is set if the result is zero and cleared otherwise. Some students are confused by this. They say, why is a zero flag equal to a 1 when the result is 0? A 1 means that yes, this is true, that the result was a 0. A Z flag equal to 0 means no, it's false, a non-zero result was obtained. The carry flag is set if there's a carry out of the most significant bit, else it is cleared. So let's take a look at some numerical examples. Let's add F0 plus 20. It's an 8-bit addition, so 0 plus 0 is 0. 15 plus 2 is 17. Minus 16 is going to be 1 as this digit with a carry out of 1. So the carry flag here is going to be a 1. This 8-bit result is not 0, so the 0 flag is false. It's a 0. 0 plus 0 produces 0. This 8-bit result is 0, so the Z flag is set. The Z flag is set to a true value. There is no carry out, so the carry flag here is cleared to 0. Let's do 1 plus FF. 1 plus 15 is going to be 16 minus 16. Gives me a result digit of 0 with a carry of 1 here. 1 plus 15 is 16. It's going to leave a result digit of 0 with a carry out of my most significant bit. So in this case, this carry out means the carry flag is going to be a 1. This 8-bit result here is a 0, so that means that the 0 flag is going to be a true value or a 1. Let's add 80 plus 7F. 0 plus 15 is going to be 15. 8 plus 7 is 15. There is no carry out. The carry is a 0, so that means the carry flag is cleared to 0. These 8 bits here are not 0, so the 0 flag is false. It is a 0. Let's discuss how subtraction affects the carry and 0 flags. The 0 flags are affected in the same manner in subtraction as it was in addition. That is, the 0 flag is set if the result is 0 and it's cleared otherwise. However, the carry flag is affected differently in subtraction than in addition. The carry flag is cleared if there is a borrow into the most significant bit. That is, if you subtract a larger number from a smaller number, the carry flag will be cleared. The carry flag is set if no borrow occurs. So let's take a look at some numerical examples. The easiest way to remember the carry flag setting is to pretend that this carry flag out here is set to a 1 before the subtraction is done, and if there's a borrow into this most significant bit, then we're borrowing from this carry flag. So let's do the 0 minus 0 is 0. 15 minus 2 is going to be 13. It's going to be a D. This result is non-zero, so the Z flag is false. There was no borrow into the most significant bit, so this carry flag here remains at a 1. Let's say 0 minus 0. The result will be 0. That means that our 0 flag will be set to a true value or a 1. Again, remember, we pretend that the carry flag is set to 1 before we do the subtraction. There is no borrow, so the carry flag is going to remain at a 1. Now let's do this subtraction. 0, 1 minus FF. Again, we'll pretend the carry flag is set to 1 ahead of time. We'll begin the subtraction. 15 from 1, we have to borrow. We've got to borrow across a 0, borrow into here at this digit. That means we're going to borrow from here. This is going to become a 0. We're borrowing across a 0. That will leave this as an F. This will put a 16 into this column. So 16 plus 1 is going to be a 17. Minus 15 is going to leave a 2 as this result digit. 15 from 15 is going to leave that as a 0. So our 8-bit result is non-zero, which means our carry flag is 0 or false. We had to borrow into this most significant digit here, so this carry flag becomes 0. For a subtraction, the combination of z equal 1 and z equal 0 cannot occur, because for the z flag to be set would mean that the two operands are equal, which would not produce a borrow, which would mean that this would be a 1 and not a 0. So this combination for the subtraction operation cannot occur. The actual way the carry flag is set during subtraction is explained by this slide. Subtraction is actually performed if we're doing a minus b. We actually do the subtraction by saying a plus the complement of b plus 1. This is known as the 2's complement value of b. We'll discuss this in another chapter. Let's just do this addition and see how the carry flag is set. So here we have f0 minus 20. In hardware, what we're actually going to do is we're going to complement 20. That's going to produce a df, and then we're going to also add 1. When we do this addition, we will find that in this case C is going to equal to 1. Our 8-bit result matches what we produce over here. And you could do it this way and determine what the carry flag is, or you could do as we said in the previous slide, where you pretend the carry flag is set to a 1, and if a borrow occurs in this digit, you set this as 0. Let's discuss shift left and shift right operations. This operator right here is the C language operator for a right shift, and here we're taking this variable and shifting it to the right by 1 position. For a logical shift, what's going to happen is all these bits are going to shift to the right by 1 position. This guy falls off the end, and we're going to get a 0 shifted into our most significant bit position. For a shift left, the opposite occurs. All the bits are going to move to the left by 1 position. This most significant bit falls off the end, and we're going to get a 0 shifted into the least significant bit. This is the C language operator for a shift left, and this statement shifts the variable I to the left by 1 position. This slide shows pick 24 instructions that support logical shift rights. This form of the logical shift right instruction shifts a memory location value by 1 and places the result back in the memory location. This is the same, except it places the result in the working register, which is W0. This takes a working register and shifts it to the right by 1 and places it in some destination register. This form of the logical shift right allows a 4-bit literal to specify the shift amount, which means that this instruction can shift by multiple positions with one instruction. This form of the logical shift right allows the shift amount to be specified in a working register. One thing to note about this slide is that the least significant bit here is being shown captured into this carry flag. So if this was a 0, after this operation the carry flag would be a 0. If this is a 1, after this operation the carry flag would be a 1. This is true only for the operations that shift by only 1 position. The carry flag is not affected by the 2 instruction forms that shift by multiple positions. This slide shows the instructions that support the shift left operation. These instruction forms here are equivalent to the instructions in the previous slide for the logical shift right operation. This slide shows the most significant bit, both the byte and the word operations being captured in the C flag. This is true only for these forms of the instruction that shift by only 1 position. These 2 instruction forms do not affect the carry flag. The PIC24 has some rotate left and right instructions as well. The rotate right through carry shifts all the bits to the right, with the carry flag shifting into the most significant bit position and the least significant bit shifting into the carry flag. The rotate left shifts the bits to the left, with the most significant bit going into the carry flag and the carry flag going into the least significant bit. The rotate right with no carry, rotate left with no carry operate the same way, except the carry flag is not involved in the rotate. The rotate right with carry and the rotate left with carry, these two instructions here, are used in the next chapter for 32-bit shift operations. The rotate right no carry and rotate right left, the rotate left no carry, are not discussed any further. The valid addressing modes for these instructions are the same as for the shift operations that only shift by one position. There are no rotate instructions that shift by multiple positions with one instruction. Let's perform a computation. Let's say that we have some 16-bit variables I, N, and P, and we want to perform this computation in C, in PIC24 assembly language. To do this, it helps to actually write some steps for accomplishing all these various operations. First thing we want to do is we can copy N and I to some working registers. Then we can compute the result of I shifted to the left by 3 positions. We can go ahead and add N to that result. We can then subtract P from that and finally write the entire thing to K. One thing we want to be careful of when doing this computation is that only the memory location K is changed. N, I, and P all retain their original values. So let's get started. We're first going to move N and I to working registers. So N would be moved to W0, I would be moved to W1. At this point we want to do this computation. So we know that I is in W1, so we'll shift W1 to the left by 3 and put the result in W1. We now want to add N to this. We know that N is sitting in W0, so we'll do a 3-operand add. We'll add W0, which has N, to W1, which has this partial result, and we'll stick the result in W0. At this point, we now want to subtract P from this. So we first got to get P into our register, so we'll move P to W1. We'll use a 3-operand subtraction, in which we'll say W0, which contains this partial result, minus P. We'll place the result back in W0. And finally, we'll do the very last thing of writing our result back to memory. So we'll do a move of W0 back to K. Notice that none of these instructions modified N, I, or P locations. They only modify K. N, I, and P locations were read by these instructions but not modified. We're going to wrap up this lecture by having a discussion of mixed 8 and 16-bit operations. In this C fragment right here, we're going to add 2 variables of 2 different sizes. We're going to add a 16-bit variable to an 8-bit variable, store the result back into the 16-bit variable. This solution right here, which takes 2 instructions, is incorrect. Let's take a look at it and see why it's incorrect. The first instruction is going to do a move that byte of U8I to WREG. That means that the least significant byte of W0 is going to get the 8-bit value of U8I. Then this is going to do an add U16P. Recall that this instruction form takes this memory location contents, adds it to WREG, which is W0, and places the result back in the memory location contents. Why is this incorrect? It's incorrect because we do not know what the upper byte of W0 is. This only affects, this instruction right here, this move that byte, only affects the least significant byte. We do not know what the value of W0 most significant byte was before executing these 2 instructions. Because this is an unsigned number, if this upper byte here is 0, we will get the correct result. However, if it's non-zero, we will get the incorrect result. So how do we fix this instruction sequence? Well, we simply have to ensure that this upper byte here is a 0 before this add is executed. There are a couple of different ways to do that. In this sequence right here, after the move that byte, we've added this new instruction, ZE, which stands for 0 extend. What the 0 extend instruction does is it takes the lower 8 bits of this register, copies it into this register, and then makes sure that the destination register upper 8 bits are 0. The reason for this is that if we take an unsigned hex number, let's say FE, then adding zeros to this does not change this value. This is the 8-bit value, this is the 16-bit value, and they're both the same result. So by 0 extending W0 into W0, we essentially place the 0 into the most significant byte of W0. So now when we do this add, we will get the correct result. The other way we can do this is delete this instruction, and before we do a move.byte, do a clear.word on W0. This will clear the entire W0 register 0, and then this instruction right here will affect the least significant byte. This lecture will discuss some of the problems at the end of Chapter 4. Before you get started, you should locate Table 19-2 in the PIC 24 datasheet that's linked on the video lectures page. This table gives each instruction, shows the assembly syntax and a description of the instruction operation. It gives a number of program words and a number of instruction cycles that it takes to execute. And most importantly, it gives the status flags that are affected by this particular instruction. This information will be needed for some of the problems that we'll be discussing. Problems 1 through 34 give individual instructions and want you to give affected memory locations and or register contents after the instruction has been executed. They also want you to give new values for the carry and 0 flag after the instruction has been executed. Table 4.6 gives initial memory and register contents, these initial register contents, these initial memory contents. It also says to assume that the 0 flag is a 0 and the carry flag is a 1 before the instruction is executed. So let's get started. Problem 3 is a subtract instruction. From this table here, we see that the affected flags, it affects the carry flag and the 0 flag. So let's do a subtraction. This is going to say subtract W0 from W1, put the result in W2. W1 has in it 806, W0 has in it 804. 806 minus 804 is a value of 2. No borrow into the most significant digit occurs. We're subtracting a smaller number from a larger number, so there's no borrow. So that means the carry flag will remain a 1 after the instruction is executed. This value right here is not 0, so the 0 flag is false or a 0. So this is the final answer. Problem 5 says and.byte W0 of W1, place the result in W1. The least significant byte of W0 is a 04. The least significant byte of W1 is a 06. Writing these in binary, we get this. Doing a bitwise AND of this, a 0 ANDed with anything is 0, so that bit's a 0, this is a 0, all these are 0. A 1 ANDed with anything is anything, so a 1 ANDed with 1 is going to be a 1. So the final result in hex, the least significant byte of W1 is 04. Our final W1 value is going to be 8004. This byte right here is unaffected. In terms of the flags, we see that the AND instruction only affects the negative and 0 flags. So taking a look at this, since the carry flag is unaffected by this instruction, because it was a 1 value on entering instruction execution, it will remain a 1 value. So a carry flag will be a 1. The result is none 0, so our 0 flag is false or a 0. Problem 11 says to clear W4. This is a word operation, so after execution, W4 will be a 0 value. Let's check the flags. Locating the clear instructions in the table, we see that none of the flags are affected. This is interesting. You would think that since the result was a 0, that our 0 flag would be set to a true value, but that is incorrect. Because this instruction does not affect the flag, and our flags were these values before instruction execution, then they will be the same values after instruction execution. So we will have carry equal to a 1 and 0 equal to a 0 after instruction execution. Problem 17 says bit clear, memory location 804, bit number 15. This is a word operation, so let's look at the contents of location 804. 804 is an 80FF. We write that out in binary. We need to clear bit 15. Well, which bit is that? This is bit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It's the most significant bit, so this bit is going to be cleared to a 0. The remaining bits would be unaffected. So writing this back in hex means that our new value of 804, memory location 804, is going to be 00 FF. What about flags? Looking at the table, we see that the bit clear affects none of the flags, so that means that our flags are going to retain their original settings before instruction execution. So 0 flag would be a 0 and the carry flag would be a 1. Problem 23 says logical shift right, register W3 by 8 positions, place the result in register W3. So contents of register W3 is going to be an F0A2. We'll write this out in binary. When we shift this to the right, we're shifting it to the right, and we're going to shift it to the right by 8 positions. That means that we're shifted, first of all, we're going to be shifting in zeros. This is a logical shift right, so zeros will be shifting into the most significant bit position. So if we take these bits and shift them to the right by 8, it means that these lower 8 bits here are going to fall off the end, and these 8 bits here are going to move into the least significant 8 bits of this word. So our final result is going to be a 0, 0. We shifted in 8 zeros here, followed by this byte here moving to this location, F0. In terms of the flag, let's take a look at the logical shift right instructions. Note that these first 3 forms here affect these flags, but we're interested in this form right here, which allows us to shift a working register by multiple bit positions. This particular form here only affects the negative and 0 flags. So that means our carry is unaffected, it is unchanged, so it will remain as C equal to a 1. In terms of our 0 flag, our final result here is non-zero, so our 0 flag is going to be false or 0. Problem 35 asks us to convert this C code into PIC24 assembly language. These are all 16-bit variables. Solution 1, which is the one in the back of the book, uses 2 operand forms for instructions. Here we're going to shift left U16J by 1 position and place it in WREG, which is going to be W0. We're then going to move the immediate hex value of 30 into W1. We will subtract W1 from W0. Recall that W0 now has this, so we're subtracting the immediate value hex 30 from that. So this is going to be our partial result here, and we're going to place that in W0. At that point, the only thing left is to add U16I to this partial result. So we'll do an add of U16I to WREG, which contains this partial result, and we'll get our final result. We now need to move our final result that's in WREG to U16K. One problem with using, while this is efficient, it only takes 5 instructions. One problem with using these 2 operand forms is that students will often leave off this statement when writing this code. If you write the code this way, it's incorrect, because what's going to happen is that's going to take U16J, is going to shift it to the left by 1, and then it's going to place that back into U16J, not WREG. In this C code fragment right here, we are not modifying variable J. We're only modifying variable K. So use of these 2 operand forms such as this can be a bit problematic for students initially. This solution shows a bit safer approach to solving this problem in terms of avoiding careless mistakes. It requires more instructions, but our experience has shown that this approach results in less careless mistakes by a student. And the approach is simple. You simply move all of your rightmost operands here into registers, then use register forms to do your computation, and then go ahead and write the result back in to memory. So let's look at this in more detail. We're going to move W0. So let's look at this solution in more detail. We're going to take all of our right-hand operands, which are IJ and immediate value of 30, and move those into registers. So we'll move I into W0, J into W1, and immediate hex value 30 into W2. W2. At this point, we'll begin these computations. We'll first do this computation. We'll shift left W1, put the result in W1. So W1 will have J shifted to the left by 1. We're then going to go ahead and add I to this. So we're going to add W0, which contains I. Add that to W1, which contains this partial result. Place the result back in W0. At this point, the only thing we have left is subtract this immediate value, which is sitting in W2. So we subtract W2 from W0, place the result back in W0, which now has our final result. And finally, all we need to do is write W0 to variable k.